All right, let's dive into the amazing, kind of hidden world of molecules. These are the things that literally color our reality and, even keep us alive. It's going to be a fun one. So, here's a question for you. Think about it. The deep red of your blood, the rich green in the leaves outside, and even the brilliant blue in your favorite pair of jeans. What could they possibly have in common? I mean, they sound completely unrelated, right? But believe it or not, they all share this secret architectural principle deep down at their core. And the answer is coordination compounds. Now, I get it, that's probably not a term you hear every day. But trust me, these structures are everywhere. They're like the master architects behind some of the most incredible things in both nature and technology. Okay, so what in the world is a coordination compound? Let's actually break down the blueprint and see what makes these things so incredibly unique. So here's the basic definition. Right at the heart of it, you've got a central metal atom. Think of it like a sun. And then, orbiting that sun and bonded directly to it, you have this array of other molecules or ions. We call those ligands. And that's it. That metal plus ligand structure, that's our coordination compound. But here's the really cool part. It's the bond that's so special. A normal covalent bond, like the ones in a water molecule, it's like a two-way street. Each atom brings one electron to the party to share. But here, nope. In coordination compounds, it's a total one-way street. The ligand is super generous. It donates both electrons for the bond. The central metal just accepts them. Chemically, we call the ligand a Lewis base and the metal a Lewis acid. But the main thing to remember is the special one-way bond, a coordinate covalent bond, is the absolute key to everything we're about to talk about. All right, so we've got our two key players, the central metal and the surrounding ligands. Let's get to know them a little bit better, shall we? Let's see how they actually build these amazing structures. So think of the central metal atom as the main scaffold, right? It's the basic framework just waiting for something to happen. And then come the ligands. They're the builders. They show up with their electron pairs ready to go, and they attach themselves to that scaffold, creating the final, really intricate complex. And here's where it gets even more interesting. These builder ligands, they're not all the same. Some have a pretty simple grip. We call them monodentate, which literally means one-toothed. And they just grab onto the metal in one single spot. But then you have the more complex ones. They're polydentate, or many-toothed. And they can grab onto that metal scaffold in multiple spots all at the same time. And when one of those many-toothed ligands grabs onto a metal, well, it forms this super stable ring-like structure that we call a chelate. The name is perfect, actually. It comes from the Greek word for claw, which is exactly what you should picture. There's this great quote that says, "A chelating ligand holds the metal ion rather like a crab's claw would hold a marble." I mean, isn't that a perfect visual? The ligand literally wraps around the metal ion, holding it super securely. This chelate effect, as it's called, creates these incredibly stable molecules, and that stability is absolutely vital, especially in a lot of biological systems. Okay, so we've got the pieces, right? Metals and ligands, but now is where it gets truly fascinating, because it turns out the way those pieces are arranged in 3D space, it changes absolutely everything. In the world of coordination chemistry, shape is reality. This brings us to this idea of geometric isomers. It sounds complex, but it's not. Just think of it like this. You have a pile of Lego bricks. You can use the exact same set of bricks to build two completely different models. That's what isomers are, the exact same chemical formula, the same list of ingredients, but a totally different arrangement in space. Let me show you a classic example. So here we have a cobalt complex. In this first arrangement, which we call the cis isomer, the two chloroligands are basically neighbors. They're right next to each other. And when they're arranged just like this, the compound is violet. Okay, now look at this. We have the exact same parts list. Nothing has changed. But in this version, the trans isomer, the two chloroligands are on totally opposite sides of the metal. And just by making that one simple shift in geometry, the compound is now green. How wild is that? And this is the whole point. Same formula, different shape, totally different reality. This isn't just some minor tweak. These two isomers are fundamentally different compounds. They have different colors, different properties, everything is different. In this world, shape isn't just a detail, it's destiny. Okay, so now that we get the building blocks, the metals, the ligands, and the incredible power of their shape, let's bring it all back to that riddle from the beginning. Where does all this chemistry actually show up in our world? Well, that deep red in your blood? That's from heme, which is an intricate iron-based chelate that grabs and carries oxygen all through your body. The vibrant green in leaves? That's chlorophyll, a magnesium-based complex that is an absolute master at capturing the sun's energy. And yep, the iconic blue in your jeans? That comes from a pigment built around a central copper atom. Blood, leaves, genes, they are all powered by coordination compounds. But the power of shape goes way beyond just color. Let me tell you about cisplatin. The cis isomer of this platinum complex is a groundbreaking anti-cancer drug. It literally saves lives by stopping cancer cells from dividing. Now, its twin, the trans isomer, with the exact same formula, remember, is completely and totally useless against cancer. Think about that. The difference between a life-saving drug and an ineffective substance is just the arrangement of a few atoms. And really, that's the most mind-bending takeaway here. It's not just about what things are made of, but how they are built. It just makes you wonder, right? If just rearranging a few atoms can turn something inert into a life-saving drug, what other incredible secrets are just sitting there, hiding in plain sight, in the architecture of the molecules all around us?